In AI interpretability, there is a well-documented vulnerability known as the dead salmon phenomenon. Standard methods are designed to show what a model sees, but these tools routinely produce plausible-looking explanations even when analyzing completely randomized neural networks. They find a signal in pure noise. This structural flaw compromises the evaluation of synthetically manipulated media, such as deepfakes. The root cause of this failure is that these models rely entirely on pixel statistics. They map color gradients and edge contrasts, but they have zero understanding of the physical constraints governing the objects inside the image. A deepfake might display perfect pixel continuity while depicting a physical impossibility, like mirrored handwriting or a joint bending backward. The statistical pattern looks flawless, but the spatial logic is entirely broken. Relying on pixel-level feature attribution provides a false sense of security. Without a physical mechanism to check its own work, standard AI interpretability remains structurally fragile. To solve this, we move beyond tracking pixels and start tracking physics using code world models. The CWM evaluates whether the state of the objects in the image obeys observable physical logic. We can operationalize this causal grounding through an analytical framework called VITA-VQ-M. To test this framework, we apply it to a physically constrained ecological system, the recovery of the monarch butterfly at the Inwood Butterfly Sanctuary. True visual veracity requires forcing an artificial intelligence to validate its visual findings against the unyielding laws of the natural world. This diagram illustrates the 6-step end-to-end architecture of the VITA-VQ-M framework. The process begins by capturing raw field images that contain embedded GPS coordinates and EXIF timestamp metadata. Preserving a strict chain of custody from the physical soil to the digital extraction prevents the AI from analyzing fabricated or manipulated inputs. If the provenance is broken, the analysis halts. This is an example of raw, unfiltered ecological input data. The system analyzes the specific green milkweed leaves alongside the yellowed, damaged lower foliage. To quantify the health of the plant, the framework applies an HSV-based green channel segmentation over the image. Estimating milkweed coverage through direct color segmentation provides a verifiable mathematical baseline. This avoids the black box opacity of standard object detection algorithms, which are prone to the very hallucinations we are trying to eliminate. By securing the exact geographic and temporal origin of the data, the system closes the first vulnerability gap in AI vision analysis. This chart maps the causal directed acyclic graph that drives the logic and dependencies of the entire system. This displays the baseline causal equation. M represents final monarch density, while K is a scaling constant from historical data. C measures milkweed coverage from image segmentation. We then apply negative multiplicative effects, P for predator load and pi for parasite load. Explicitly programming these biological limitations prevents the model from hallucinating an impossible ecological outcome. If the milkweed coverage is 0, the equation guarantees the monarch density is 0, regardless of the pixel patterns. This image shows the nonlinear temporal extension for the model, which accounts for ecosystem changes over time. The alpha coefficient represents the logistic growth dynamics that occur under active, human-led habitat restoration. For complex physical systems, a single-point prediction is scientifically insufficient. The variables in a living ecosystem constantly fluctuate. To solve for this, the system generates 1,000 bootstrap resamples of the vision outputs. This converts singular predictions into a full posterior distribution, creating specific, bounded confidence intervals. Forcing the AI to perform explicit alternative hypothesis testing and produce strict uncertainty bands eliminates the mathematical fragility found in standard interpretability. This interface shows the ecological varigraph, the front-end execution of the code world model built in Marimo. Interactive sliders allow researchers to perform real-time scenario testing by adjusting the ecological predictive vectors and tracking the resulting percentages. The UI demonstrates multiplicative sensitivity. Increasing the milkweed coverage from 40% to 80% yields a 3-fold increase in the projected monarch density. These calculations are tied directly to the physical reality of the predator variables the system evaluates, such as ants and wasps hunting in the foliage. Reactive visualization maps abstract equations directly to biological outcomes. exposing the illusions of standard static feature attribution by demanding cause and effect. We can apply this rigorous physical logic to a specific real-world conflict. Municipal park crews routinely eradicate native milkweed, despite protective state legislation. This eradication policy stands in direct contrast to the restorative biology at the Inwood Butterfly Sanctuary, boasting a 98% survival rate for caterpillars. This chart simulates the macro impact of these opposing policies over 10 years, showing the divergence between the red trajectory of eradication and green trajectory of sanctuary intervention. Explicit 95% uncertainty bands reinforce the model's statistical rigor, providing verifiable data to counter destructive policies. Grounding algorithms in the unyielding laws of the physical world provides the only path toward true AI vision.